Okay. Um, I want to welcome everyone to the August meeting of the Houston Functional Programming User Group. And tonight I am delighted that we have Eric Norman back. Eric at this point is a friend of the group, having presented numerous times over the years. And his talks are always super fun and uh, we have lots of stimulating discussion and some arguments and a little bit of, you know, I don't know, back and forth. And that's always excellent. And so I'm really looking forward to uh, Eric presenting to us again tonight. So, Eric, the floor is yours. Thank you.
Cool.
Welcome.
Thank you, Claude. It's always fun to be here. Um, it's like a tradition, and I see a lot of familiar faces and some new ones, and um, it's also I enjoy presenting to this group because there's a certain continuity to it. As the ideas in my book have evolved, I try them out here, and I learn a lot just by the reactions that people have. So I hope that I don't have to change anything this time because I don't want to rewrite my book another time. Um, but I'll just get started now. This one is going to be um, much more of like the technical theoretical background behind domain modeling and sort of the theory of why it works. Um, I don't want to get too much into this in the book. I want the book to be much more a practice. Um, so this is like sneak peek behind the curtains because when you write a technical book, you kind of have to have the background that you don't share because that always gets dry. It's not interesting. People just want to know how do I program better. But it's got to be there or there's nothing hanging everything together. All right, so I'm going to share my screen and we can get started. I'll just share this window. Okay, so we can all see this. Um, sorry, let me go back. So this talk is titled On Domain Modeling. Not very creative. I'm Eric Normand. I wrote this book, Grokking Simplicity. It's about functional programming. It's aimed at beginners and people trying to help mentor beginners. So if you are interested in it, the first link will take you to Amazon. The second one will take you to the Manning site. And that code next to it, TS Simplicity, will give you 50% off if you're interested. That's all I'll say about it. Except also that the book that I'm writing now was supposed to be part three of this book, but it was just getting too long. And I'm glad I didn't put it in there because it's also taken me since this book was published in 2021 to get to get the material ready. Okay. So we use this term a lot, abstraction, and I use it a lot. And I went down a rabbit hole because I realized that I was using the word and I didn't really know what I meant. And I started asking people what they meant and got all sorts of conflicting answers. And I started looking up definitions for it and searching in computer science texts. What do we know about this word? What is it? And I went so deep that it started becoming painful when I heard people use it because people use it in different ways, sometimes even in the same sentence. And it's like you're not I can't talk to you because they would have to have a 2 hour discussion about the words you're using. And I just, you know how it is. You have to just kind of like go with the vibes and like I know what they're saying, even though they're using the words wrong. So that's where I'm at with abstraction. I've gone way too deep, but I've found a good definition that is actually, um, it is one that is used a lot in mathematics, and it's the one that I'm going to share right now. Okay, so I I have given this little section before in another talk, so please bear with me if you've seen it. But let's imagine you've got a group of sheep and another group of sheep. You want to figure out how many there are total. One way you can do it is you can count the two groups and you get the numbers 3 and 4. And then you can add up the numbers 3 and 4 and you get 7, obviously. But there's another way you could do it, which is you can smush the two groups together and then count the big group that results. But when you count it, you get 7, which should be the same answer, right? So this is like a little microcosm of abstraction. Um, there's a real world situation that is a concrete domain, the sheep. We perform an operation on them that maps it into a concept. In math, they also call it an object in the abstract domain. So that's the number 3 or 4 or whatever number you do. And then there's these operations that operate on those objects in the abstract domain, such as addition and multiplication. We're using addition. Now, the reason we get the same answer in both situations is because addition corresponds to the group pushing, smushing together operation. And that means that any path through this, starting from the bottom left to the 7, will get you the same answer. So the bottom left to the top right, you can go up and to the right, or you can go to the right and up, and it'll get you the same answer. That is the key to everything we do because we take real world situations, we map them into a digital domain, this abstract world of concepts. Maybe that we got records and functions and stuff. And we hope we get the same answer out at the end of the day. Um, this is like the secret to why computers can do work that is important to humans, right? It's not just calculating stuff. Okay, so this is also known as a homomorphism, with an asterisk on it, which we'll talk about in a second. But the homomorphism means that that add operation and the group operation will get you both to the top right. Doesn't matter which way you go. Um, that when you do this mapping from the bottom to the top, you can do the same operations. And then we can also do this other thing, which is like, let's imagine a situation where like you give someone your two groups of sheep, and then they get mixed up with a whole bunch of other sheep. But they recorded, oh yeah, you gave us 7. And now it's time to leave the sheep daycare. And you're like, okay, give me my sheep. They're like, okay, you need 7. They count off 7 and give you 7 arbitrary sheep because they didn't really keep track. And this that number 7 does not tell you which sheep um, you had. So you get 7 sheep, and if sheep are fungible, that's okay. So we need a way to interpret this number um, back into sheep, into the real world, right? So I'm calling that choose because you choose 7 sheep. I didn't have a better word for that. And then this is a right inverse. It's not a full inverse of the count operation because it's lossy. Like the count is lossy, loses information. It loses which sheep did I count. Um, and so once that information's gone, but you can come back down. So it's a right inverse, not a full inverse. And so the abstraction is that up arrow. It's the mapping. from the concrete domain to the abstract domain. That is what mathematicians call the abstraction.
Wh which up arrow or both because they're both count?
Well, they're both count. Yeah, they're both an operation. They're the same operation. Um, but it's the mapping. So, in this case, we're mapping from a collection of objects to a number, but you could map from a person to a row in a database, right?
Would it
And
still be an abstraction if you took sheep to like seven apples, right? Like so another concretion, right? Another like concrete object. I'm just kind of thinking, trying to
so you're
understand this.
saying you do like,
Well,
I'm corresponding each sheep with an apple.
yeah, is
That is
that
not that is
that's
not
not
an
that's not an
abstraction.
abstraction because
That
it's
is right. I mean, that is a very, they're both in the same concrete world, right? It requires going to a more abstract world where the operations are mental, basically, mental operations. Um, but I mean, I
yeah.
don't want to jump
That's why
the
I was
gun
asking.
on that.
That's why I was asking the question. I didn't mean to like derail,
But
but
you
it's
can,
interesting.
I don't have this slide in here, but if you weren't good at addition, you couldn't do 3 plus 7. You could go back down by choosing 3 fingers and 4 fingers. And now you do the group on the fingers and count your fingers, right? And the counting would go back up to the abstract domain. And you would expect to get the same answer, right? Because in some way, objects are fungible when you're just counting, right? So it's interesting that like we do this up and down abstraction back down all the time, right? Okay, let's go a little bit deeper into homomorphism. It's um oh man, I read too much about homomorphism, but it's interesting. It was the homo in homomorphism means same, but it was actually a mistranslation of a German word that actually meant similar. So it means similar shape, similar form. It's supposed to, but it's historical accident. It was translated as homomorphism, which means same form. But it's basically a mapping that preserves the structure. So the structure is that 3 plus 4 equals 7, and at the bottom you had 3 sheep and 4 sheep groups into a group of 7. That's the same structure. And we, as humans, have discovered this abstract idea, invented this abstract idea of number that works with any object, right? And the structure, it can you see my mouse if I move it? Okay. Um, this is eh, a like JavaScripty way of writing what we did. So you take X and Y, the two groups of sheep, and you group them together, and then you count that. That should be equal to counting the X, counting the Y, and then adding those two up, right? So turned into a more mathematical notation, you have if you do the concrete operation X, circle X on X and Y, and then map it into your domain with F to your abstract domain, it's the same as mapping the X and Y and then doing the abstract operation. So the mapping is F, and we are looking for a way of satisfying this operation or this equation, sorry. Um, we need to figure out all the operations that we can do in the concrete domain and have equivalent operations in the abstract domain so that this is true for all of them. That's what we're doing when we're building software. Um, I want to say that you must do this or the software won't work as you expect. Um, I don't, that's kind of strong. But I do want to say that like domain modeling, the way I'm defining it, it means writing software, but keeping this left-hand side in mind, that there is this concrete operation that your abstract operation has to satisfy in this equation. right? Like we often forget this and we just start refactoring the functions in our code without recourse to like, well, does this correspond to anything in our concrete domain? Okay, and then the right inverse. Oh, and please stop me if I'm going too fast or if you have a question or anything. Um, okay, the right inverse is of f. We'll have a g. So this in our case is terrible JavaScript code, but it's the way it has to be written. There's this operation choose, right? So what we're doing is saying, look, if I take this right hand side and I choose, meaning I choose the sheep, so I go back down, I'm like inverse mapping, um, then that's the same as counting and then choosing on both of the groups and then grouping them together, which is more roundabout way of getting back to the group that you had at the bottom. And so this is a way here of expressing that. F of x is just x up in the abstract domain. So this is saying you take two things from the abstract domain and you apply the circle X operation on them in the abstract domain, and then you map it back down. That should be the same as mapping them down first and then applying the concrete operation. And of course, we want a mapping G back down because that is how we interpret the situation that we find in memory or in the database or wherever. So this one is about taking the real world and putting it into our software. And the other one is about now it's in our software, we run it, we see what happens, like it's going to get some result. And then now we have to interpret that as like meaningful in our real world. So that's what G is.
Okay, so
Yeah.
can I ask a question? I'm trying to make sure I'm following you here.
Hmm.
So um, are you then saying that your definition of abstraction, or the definition of abstraction, you've done all the work, um, is it's essentially it's mapping something what in the real world, concrete, into, and that I think that's what I
It so it's mapping something from one domain into
okay,
a more abstract domain.
okay,
And
but
that
I
abstraction is the loss that's included in the mapping, right? So the
that's interesting. Okay. I mean, I understand what you're saying about information loss. I think I've often heard abstraction, and maybe it was you, I don't remember now, um, talked about as making things more precise as
sure,
well.
yes.
Um, but you would say it's about moving essentially from one domain to another,
Yes,
and
with the loss of information,
with some loss of
right? Which is
information.
why the sheep to apple doesn't quite work. Because if you're doing a one-to-one correspondence between sheep and apple, you can always go back. You haven't lost any information, right? Um, you have to lose something. Um,
Uh-huh,
and like the number three does not tell you what you counted, right? So that's why, it's lossy.
uh-huh, uh-huh.
Yeah.
Okay, and so the other part that I'm hearing here is essentially your definition of programming is about this movement between the what we could call the real world or
Mm-hmm.
the concrete world
Mm-hmm.
and this more abstract domain or something. I'm still not sure what to call it,
Yeah.
but that domain. And so you're very concerned about sort of that movement back and forth
Yes.
is fundamental. And
Yes.
which separates it because someone could be doing sort of pure comp sci or something, right? That has not
Right.
that isn't relevant to the real world.
Right. They're just
And
building some formal system in the
mhm,
sky and seeing what properties it has.
mhm,
That's totally possible. Yeah.
mhm. But that's not what you're when you're thinking about programming, that is not what you're
Right.
thinking
So like
about.
usually in industry when we're programming, it is some real world situation that we're basically making automated bureaucracy about like the, tracking and information about it and maybe controlling it a bit, right? But it's yeah. Yeah, it's like some real world thing that your software is about.
Cool. Yeah,
And
thank you.
and so for the right inverse, I'm just kind of thinking
Hmm.
about this. Do you have to like would you have to like label the sheep 1 through 7 to get this right inverse? Because I'm kind of
It
seeing like
mm,
if you chose count of 1 and count of 0, then that should be, if you choose that 1, that should be the same as, well, let's see. Sorry, I'm trying to think it through. Um,
so the reason it's a right inverse, maybe
sure,
this
sure.
will help, and not also a left inverse, um, is that if you start with a number and you choose 7 sheep, arbitrary sheep, but then you count those 7, go back to the number 7, you're back to where you started exactly 7. So that is a real inverse on
I
that
see.
side.
I
But
see.
if you
So
go the
going one
other
way. Yeah,
way,
yeah. Okay, no, that makes sense. Yes, yes.
if you count them first, and then when you come back down, you don't know what sheep you had. So it's lost something. So it could like, and in some domains, it might not matter, right? Like if someone's like, you know, can I borrow $10? When they give you back the money, you don't care if it was the same bill, right? Like it's fungible. It truly is fungible to you. Um, and so it might be a full inverse in that case, right? But usually we're talking about identifiable things like people and things like you want to keep track of your kid. It's not just I want a kid back at the end of the day. Like you want the same kid. Okay. Any other questions? All right. All right. So one of the challenges in this, this is kind of a big challenge, is making that equation work. But you need to understand the domain at the bottom, and because you need to map it up, so you need to know what you're mapping. And so there's actually a lot of work done on this. Like it's sort of weird. It's like a formal way of presenting a system that you're trying to formalize. Okay, let's go into it. Okay, so it's actually a really simple model. So you have something that's in some number of states, right? So if you were talking about a lamp, we could say, well, it's either on or off, but then the light bulb might be broken or working. And like you could even add more, like maybe the wiring is working or broken. It's plugged in or not. There's all sorts of um, things that this lamp could make it not work if you turn it on, right? And then there's this other set of things called the observables. These are the things that you can actually observe. You can query the system to know the state of. And they might correspond to the variables, but they also might overlap with them, so you're not really sure. So if you do ask, is the lamp shining right now? And it is, everything's working. It's plugged in, the wires are connected right, the bulb is working, and the switch is on. But if it's not, uh, it could be any one of those things is not working, or some combination of things are not working right. So then you got to go and like observe other things. So the switch, is it on or off? I'm going to shake the bulb. If it's tingling, I'm pretty sure it's broken. But If it's silent, it still might be broken, but I'm not sure, right? So there's all these things that these are the things that we actually get to see, and we are not privy to the variables underneath, but we know they're there, right? We just can't get them directly. We can only go indirectly through these observables. So our job often is to figure out what these variables are, um, even if we can't really look at them directly. Because these variables are going to model the system way better than the observables do. The observables, you need some like crazy logic sometimes to figure out what's actually happening. So an example of this might be something silly like someone fills out a form and like there's data entry and you know their full name, but you need to know, you know they have a first name and a last name, but now you have to parse it. You have to like break it on space. You know, you're trying to figure out some fungy thing to fudging the data to fit it into the first name and last name, right? And that was a very simple example. It happens all the time. All right, any questions on this? Because I think this is just a very simple, it's like a formalization of the messy systems that we're dealing with all the time, the messy domains that we have to deal with. Usually your domain is going to have a ton of variables and different states, and your observables also, you're going to have a ton of them. Okay. So that was the domain, like the concrete domain. What I call that's the domain that you're modeling. What do we model it in? A formal system. So the formal system is actually a really fascinating idea. The idea of formal system is that it has um, much less meaning than the system that you're modeling. So an example of this is formal logic. You take all your statements of truth, like, John likes pizza, and it just becomes A. And then, John likes soup, and that becomes B. And it just totally losing any meaning, just represent it with a symbol. And now the A could be anything, right? So it's a lossy mapping, right? You are losing information. But now because it's A's and B's and you have all these rules of inference about how you can combine them, you can actually get a result out the end because it's a simpler system to study than if you're studying a system that also includes pizza and soup, I guess. But some meaning is preserved, right? So the meanings of like the special operators like or and implication and negation, those kinds of things are preserved in the formal system and often tightened up and made like precise so that they can be manipulated um, more or less syntactically. Okay, so a formal system, simple way of looking at it is it has this syntax of symbols, mostly meaningless, but some of them have real meaning, and then a grammar for combining those symbols into a string. And then it has semantics, and that's the axioms, which are the things that are just considered true. So is statements in the language, strings of, grammatically correct syntax that are considered true, and then rules of inference for finding new things that are true based on other things that are true. And the cool thing is that JavaScript fits this. It is a formal system. Any programming language is. It has syntax, things you can legally construct in the language, and it has a semantics to it. And interestingly, the semantics are defined more or less as like, okay, you're in this certain state and you do this statement and you're now in this state, right? Most of them are. A lot of them are about, output and stuff, but um, it is a very complicated formal system. But it's formal enough that we can use it for this kind of modeling. But another thing that's interesting about it is that we're not inventing a new formal system. Mathematicians will often invent a new set of symbols and operators between the symbols and the axioms and stuff, because they're working on a sheet of paper. They're trying to keep it tight and contained. We've got these general purpose programming languages where we're kind of using the existing semantics and we're able to create a little bit of our own on top, right? So we can define new functions, we can define new types, things like that. But we're still reliant on the type system that we're using or the execution semantics that we've got. So it's kind of interesting because a programming language is almost like a formal system for creating a new formal system, right? This is going back to like the first Turing paper where he shows the universal Turing machine, the Turing machine that can run other Turing machines. Um, there's something there that is really fascinating, and I think um, I don't know, it blows my mind every time I think about it that we're working in this cool domain where we're that, that we're building stuff out of like an infinite loop like of like recursive. This thing can run on itself. It like it's crazy. Ah, okay. So what is the whole domain model? This is like laid it out a little bit more abstractly. So the bottom we have our domain. It's got the different states and then actions that will transition from one state to another, right? So maybe it's turn on the lamp, something like that. The state is like the combined state of all the variables for that lamp. Now we map, oh, and that's the states and observables. We map that into code. This is our formal system. Um, and usually we represent states as data. That's the usual way. I'm not going to go into the code and data dichotomy and stuff, but so I'm simplifying. But like we map it into data. And then we map actions on that data into functions. And so we have this, data one that represents the state of the lamp into data two. And we want to preserve we want to maintain the commutativity of this diagram, right? Meaning I can take state one, go to data one, apply the function, get data two, and then come back down, and it should be the same as state two, right? Or whatever path you can take through this, you should be able to wind up in the same state. And then, of course, there's this mapping that is also part of the model. So really the model is the domain model is the mapping and the code. Like what does it mean?
So,
Like, oh, yeah, go ahead.
sorry, no, I really like this philosophy, but the domain is sorry, the domain is the sheep.
Yeah, sure.
No,
Hmm.
I mean like that's the concretion, and the code is the
Yeah.
abstraction.
If you're
Okay,
writing code to track sheep or
sure, sure.
account for sheep or whatever. Yeah.
Okay, no, I
Yeah.
like it. It's cool.
Yeah. Um, okay. And so here's this thing where I hope to blow your mind, although this is a very basic diagram. This is a thing that I've been playing with for about a year now. Um, I talked at the beginning about how we use abstraction in too many ways for it to be a useful word. Um, and one way people use abstraction is they say, I'm building up abstractions, right? The direction is kind of arbitrary, the up or down, right? We tend to think of up, like I imagine, what is it Raphael's, um, the Forum? It's a painting where there's all these philosophers and Plato is no Socrates is pointing up and Aristotle is pointing down because Aristotle was interested in the real world and like categorizing it, and Aristotle was interested in ideal. Maybe it was Plato. I can't remember, but he's interested in the ideal world, right? So we have this kind of bias that like abstract stuff is up, concrete stuff is down toward the earth, right? So that's the direction I tend to choose. But we often talk about I'm writing code, I'm going to build a new abstraction up on top of the code I have, right? Really, what we're probably saying is an indirection, right? But we think of the machine as like the lowest abstraction that we've got, right? It is lower in abstraction. But in fact, the machine is the most abstract. The machine can run any program. It can run it about sheep, it can run it about coffee and pizza or whatever. It is totally formal and that has no meaning except logic gates, right? And mathematical operations like addition and what have you. It's got that built in. But that is the most abstract. And so I've been playing with this for a year of like really trying to think of the stack of abstractions going the opposite direction that I was used to thinking. So you start with your domain at the bottom, and you map it into code, so data and operations. And then the compiler will map that into machine code, which is even less. It's an abstraction because it's lossy. You're losing the variable names and, all the human meaning that you might have left in your code. And then the machine code will get executed in the machine. It's basically just encoded as electrons in logic gates, right? And then we have to go back down the other way. So this idea of the machine as a formal system that we are mapping up into has really changed my view of like what we do. I mean, who here thinks about, I mean, a lot of people do. So I'm not saying that nobody does, but I certainly don't think about the particular machine that my code is going to run on. My stuff, the stuff I do at work runs in the cloud, and like I'm not responsible for that at all. I only think about one level up, which is the language I'm writing in, and that it compiles, and that's it. It is it is like now somebody else's problem. But that means it's this abstraction, right? It is a thing that I don't have to think about. Um, And anyway, I want to present that to you because it's been kind of mind-blowing for me to think about this. It's truly the reversal of how I was taught about it. I think the first hints of this for me came about when I was writing my book and I was talking about um, the different layers in the stratified design. And what can we learn about this diagram and directionality of it and stuff? And um one of the things that I talked about in the book is how as you go down you get more general. At the bottom we had the computer, the programming language, these are all very general things. And then you're building stuff up and you're getting more specific. Okay, now this is about my business. This is about this specific business case. Like it's very small. This is about like the button in the GUI. It's all like the stuff at the top is not the most abstract. People think of it as the most abstract because they've kind of lost track of what the computer will do with it, right? Like it's going through so many indirections, it's impossible to know like which, is there how many times is the adder going to get run, that kind of thing. What machine code is this going to actually execute? It's impossible to know that. But that's not that's not what abstract means. Abstract means it does not mean I can't it's it's too complicated for me to know what's going to execute. Abstraction is actually in that diagram going down. Um, okay.
So I
So
think
yeah.
this is really interesting, and I think one thing I just want to bring up right now very, very quickly, and we can talk more about it later. But so a lot of what you're talking about maps on to my work on measurement and measurement theory. And
Hmm.
so in measurement theory, we basically have our indicators, our concrete real world things that emit signal, and then we have our latent variables that we're, you know, trying to construct in our concepts and all that. And just in that model that you just presented, we have the same thing where there's sort of question about should the arrows go up or down to link those.
Hmm. Hmm.
And in the paper that I was working on with a colleague recently, actually, I don't know, maybe a year ago or so, but we made it horizontal
Oh yeah.
because, right? Because we
Just
wanted to
punt.
just, yeah, basically, we wanted to get out of that vertical thinking that has sort of captured everyone so much and say one isn't higher or lower than
Hmm.
the other. One isn't better or more important. They work together. And you need both sides of it. And then the other thing that we've really struggled with is can we even get rid of the arrowheads? Because at this point in my career, I
Mm.
don't even know what the hell an arrow means anymore. Because
Uh-oh.
people use it like the word abstraction. As you're saying, they just use it all the time, willy-nilly. People
Yeah.
use arrows all the time. And so I've gotten to the point where
Mm.
I'm just like, what do you mean by that arrow? And
Yeah.
it is that kind of thing. The same thing when you were talking about abstraction, and like, I'm not even sure I can have this conversation with you because I want to know what you mean by arrow. Right? What that you drew that arrow, and I know
Yeah.
it means something, but I honestly don't know anymore. And I suspect you don't know what it means either.
Uh-huh.
So anyway, I just wanted to say that like I've gone through this sort of similar process in this other domain.
Yeah.
And so it's super interesting to me. So
It's
that's
the
all I'll say right now, but we can talk about it later.
sure. Sure. I'm gonna add, oh, you can't see my screen anymore, can you? I'm going to I referenced this painting, so I want to share it. I looked it up. It's Raphael, but it's called School of Athens. And you see Socrates or Plato, I can't remember who, is pointing up, and Aristotle is kind of pointing down. This is one portion of it. It's not the whole thing. Um, there's also a part where one of my favorite parts is here, I'll move this over here. It's this part here where this is Euclid showing his geometry and like he's pointing down. He's like drawing pictures on a piece of on a stone on a slate. But then there's this guy here in the middle who's like looking up like he's having some kind of abstract rapture based on what he's seeing on the chalkboard. And he's pointing down, you see. He's like pointing to this concrete thing that's giving him this like abstract epiphany. I don't know. I think it's really great. It really showed that Raphael was a master of this kind of symbolism and knew all this cool stuff also. Any other questions?
I do have one. So I'm still kind of trying to get the concretion to abstraction. So in math, there's a concept of something called a universal property, right? And I think this is similar to what you're talking about, where you have like, if I count something, right, I can define a basically some sort of function from things that I'm counting to a count, and I can certainly define something back. But the problem is that if I change the set of things that I'm counting, or if I apply some other morphism to the things that I'm counting, I won't necessarily get the same thing back, right? And I'm thinking of it kind of like, I mean, maybe a simpler example for a computer scientist would be something like, a list. In some ways, using this could be abstracted by a hash table, and then a hash table could be abstracted by a count, right? Because
Like a
somehow
link.
lists, you can reorder lists, but then if you pick an ordering, so if you go from the list to the set to a hash table, and then you choose a mapping back to lists, you're picking and ordering. So
Right.
if you try to go through like the reordering and then try to go through this thing, you sort of lose this
Happens all the time, right?
yeah. But the same thing's true of sets, right? So if I have two
Yeah.
sets,
You
they
lose the duplicates and the
yeah
ordering. Yeah.
yeah, and but if you have sets, then you could have a morphism between two sets with if they have the same number of objects, right? You can say like, well, this set goes to this set. I'm just relabeling things, relabeling my sheep to my apples. When I count that, that's more universal because counting, it doesn't matter if I relabel things, it's the count's always going to be the same. But
Uh-huh.
trying to pick the specific objects for that set, I could end up with a mixture of sheep and apples and, but I mean, I really like this approach. I'm just kind of trying to think through and I think universality might have something to do or universal objects in the category
So
theory of
what
math.
does universal objects mean? What
So
is
a
that?
universal object is in a category. In this case, you have a bunch of arrows. So I'm thinking of these arrows as being functors, but they're really
Yeah.
they're just a way of getting from basically defining an abstraction from one collection of things to another collection of things.
Mm-hmm.
A universal object would be something that if you have a bunch of arrows, kind of a bunch of functors between things, or I guess like it could be in the case of just let's just say set functions. If we have, let's see, if you have two functions that map to the same set, the universal object would be, in that case, a function, something that maps to both of those things. So it would be a some sort of product. So it'd be like if you have sorry, it's tricky, but if you have in this case, if we have apples mapping to a set and sheep mapping to a set, there's actually a universal object for both of those mappings, which is we have a mapping for sheep, we have a mapping for apples, we get a mapping for the set of sheep times apples, right? So any pair of a sheep and an apple, we can map that to this set. So it's kind of like there's some different ways of I guess in that case it would be the disjoint union of sheep and apples, not the product. But there are ways to sort of construct things like Cartesian products out of limits in a similar manner. But I think that would be limits going the other direction. So I just was I'm sort of thinking about it. It's not a fully fledged thought yet, but I'm really excited about this approach.
Yeah, cool.
Well, and Chris really likes sheep, so.
I like sheep. Yeah, they're cool, man.
Yeah.
They're great animals.
Um, Nick, could you say what more about what you mean about the in the chat about abstraction going in the opposite direction of emergence? I was curious about what you said there. Actually, let me start. Eric, do you have more to present, or
Nope.
was that sort of the end? Okay.
Nope. I
Okay.
mean, no, that's it. That's all I wanted to talk about. I can go deeper into anything if anyone wants to, but let's go. Let's open it up.
Yep. So what we'll do just is we'll do a little bit of discussion with the recording, and then in a few minutes I'll turn off the recording, and then we can continue the discussion with the recording off. So yeah, Nick, could you say a little bit more? Because I was really curious about your comment in the chat. Okay, maybe they can't. So I'll open it up. Other questions or comments about this?
I think it's I really like this way of thinking. One of the reasons I like it, and for like not a stupid, but a programming concern, right, is that having these kinds of this kind of abstraction and sort of thinking of things in terms of like an algebra of actions or something like that, I think really informs how you can test your system to see how it works, right? Like you simplify your domain, like the processes and the observables in your domain, and it gives you a lot of good instruction on, okay, so what rules should these things have, for them to behave properly? So maybe that's even a further abstraction than your code, right? Because you're using this sort of further abstraction as a way to test the implementation of your algorithm in your code. I just think it's a really useful way to think about correctness in code.
Yeah,
I think that's really
I think
important.
there's something really interesting there. Um, one of the ideas that I'm writing about in the book is that you can create these formal domain models. And usually when you create them in your programming language, they are not realistic in the sense that they like aren't hitting the database, they aren't hitting your APIs. They're just in memory, right? You're just using data in memory, but you've got the behavior right. Right? You can work in memory like I like to work at the REPL and just like figure it out, get it right. And then you have an oracle, a test oracle for how the system should behave even when you're hitting the database. So if you do have to store it durably instead of just in memory, like these properties should still apply, modulo database access errors and stuff like that, right? But you should still be able to, you should be able to run your formal model in memory and compare it against the behavior of the actual implementation that uses the database. And the cool thing about that is like you can just put it through its paces. You could just run any, I mean, in theory, any combination of commands that are valid, You could just run them both and see if they give you the same answer. So you can do like you can sample that with property-based testing, right? You can just generate a subset of all possible sequences of actions that would happen, and you have an oracle for it. And it's much easier to get that one right than the other one, and so you're getting some leverage out of it.
I also think this kind of abstraction, it's useful for thinking. I mean, I like the concept of using this to think about sort of the concrete world of buffers and things like that. But for example, right, this concept, we have a concept of an abstraction from a buffer to a length of that buffer, and this fails terribly when the buffer gets too big, right? Because then
Hmm.
addition no longer works, and
Yeah.
it's useful to understand the edges of abstraction as well. I mean, I think that and a lot of interesting, horrible but wonderful bugs come out of that.
I mean, those kinds of things are like, to me, they come out as like engineering decisions. It's like how
Yeah.
big of a group of sheep are we gonna have to count? Because if I use just a byte, I only get 256 states, but I actually probably need thousands or millions. And so like how many am I gonna have to count is becomes a real question. Because our formal systems do have limits, right? Our machines do. Um, in the in a very similar way to how you can run out of fingers and toes to count on, right? Like you just run out, and they have defined behavior when you overflow or whatever, but they might not be the behavior that you want your system to exhibit. So yeah, that's I mean all that stuff is like I think the cool stuff of engineering.
So I had a question about um, this idea about sort of losing information, because I bristle with
Hmm.
that phrase, and I guess I want to like either ask or push you on it a little bit. Um, is it about losing information, or is it about selecting the relevant information?
Sure.
It, or are those the same thing or a different thing? Or how important is this idea that you've lost information? Yeah, how important is
I
that idea
mean,
versus the selecting what is the important information that is relevant to whatever the problem you
well,
are dealing with? And often we get that wrong, right? And then we go back and we're like, oh crap, I didn't collect the information I needed.
right. I can't do this operation because I didn't collect the, yeah.
Hmm.
Um, so my question is a question back. Like, what's the difference? Because you are constructing this mapping. So you are choosing what's being lost and what's being preserved, right? And you can't preserve it all. It is not possible. In at least in the practical software that we write. So you do have to select what are the important things that will allow the operations in the abstract domain to have the same results as the concrete operations would, their corresponding concrete operations.
I mean,
That's so you're losing it, but you're also making sure to not lose the important stuff.
well, so and Wesley put in the chat, isn't losing information the basis of abstraction, taking away that information that you don't need to model what you are working with? And so, right, I do a lot of modeling in my work. I teach modeling. What I what I generally argue is, as you just said, Eric, when you're constructing a model, obviously it is simpler than the real world. It has to be,
Hmm. Hmm.
right? That's the whole point. And so you're selecting to retain that information or to capture that information that is relevant to whatever the problem you're trying to deal with. And so what I would argue is if you do it right, you're not losing information because that information was irrelevant
Mm,
to the problem that you're trying to deal with.
yeah.
Right. And that is a subtle difference.
Yeah. But
Um,
but the information is there in the concrete domain, right? Like just because you don't capture your user's, you
mhm.
know, height or whatever, like it's still there and you can't recover it from the mapping down, right? So it's I mean, I think you're putting maybe a fine point on this idea that you are definitely constructing this mapping to serve your purposes. It's the same with the operations. There's some operations that you do not care about, that you are just not going to, they're not relevant to the software you're writing. Um, and it's the same as when you're like picking those variables. There's a lot of variables that you're just not going to even write down because they're not relevant to you and they're not going to even figure into your mapping, right? Um,
So when you have like
yeah,
a right inverse, though, doesn't that kind of protect you, right? Because you have a concretion from your abstraction, right? You have a way to get back into the real world. And so, I mean, you might be losing some information, but at least you know that you're doing something that has some basis in reality.
right,
And I think that's where that or at least in my understanding, that seems to be where that becomes very important in
right.
the model.
Yeah, yeah, yeah. And there's tricks that we've learned that maybe like the more I think about it, the more I realize like, hey, we're actually pretty clever. We know this stuff. We just don't, I don't know. It hasn't been put quite this way. But like when you give someone a like a username and password, right? That information is in the person's head, right? Or, some way it's written on a post-it on their computer or whatever. So it's a way of reconnecting this database record, this database row with a particular person. You can email them. So there's like a practical real world thing with their email address as their username. And then the password is a way of double checking that it's the same person that created the password, right? And if it's this law, that's leaky, someone can steal their password, whatever, but you're trying to get back to a real person. And it's a cool trick that we have. It's like it's putting some piece of information into their head, so it's in the real world, and yeah, it's like if you numbered your sheep, right? You just like branded a number on them or you tattooed them or something. Like now you have some real world thing that I can use in my abstract system to track them, to count them, to, whatever I'm doing with the sheep.
Yeah, but if I need to go through two-factor authentication to get my sheet back, I'm going to be really irritated. Um, all right. This was great. I want to stop the recording in a minute and continue talking if you've got a little more time, Eric. I've
Sure.
I've
Yeah.
I've I've got some questions for you. But does anyone have any last questions that they want on the recording? Okay. If not, then I'm going to say thank you so much, Eric. This was fantastic as always, super interesting. Um, so thank you so much for being here.
Yay. Thank
Yeah.
you. This was fun, as always.
All right, now we're going to turn off the recording and have the real conversation.